So in the last session, we proved three important sub-results on our way to study the Sylow theorem. And those are these three. Let G be a group of order p to the power of n, and X is a finite G set. Then the number of elements in X is congruent to the number of single element orbits in G. That is the first one. The second one is Cauchy's theorem. That says that G is finite and P is a prime that divides the order of G. Then there exists an element in G that having order of P. Then the third result is a group is a P group if and only if its order is a power of a prime. See, in Sylow's theorem, what we are planning to do is to characterize non-abelian groups. In an abelian group, every subgroup is normal, but not in non-abelian groups. So our next attempt is that if H is a subgroup of G, H doesn't need to be a normal subgroup of G, but if H is a subgroup of G, then find the largest subgroup of G having H as a normal subgroup. See, if you take the group here G and there is a subgroup H, H is not normal in G. But that our next attempt is to find out another subgroup of G for which H is normal. Of course, there is definitely one that is H itself. So, and that subgroup is called the normalizer of H. And that is our next attempt. So, let G be a group and HB a subgroup. Then let C be the collection of all subgroups of G. Our idea is to find out the largest subgroup of G for which H is normal. So it should be in in this collection. Now we are defining a map. Define a map from G cross C to C by G of H is equal to G H G inverse. So definitely GH G inverse is a subgroup of G. So this definitely belongs to the collection C. Then it is easy to prove that this map is a group action. The only thing which we need to prove is take two elements of this, G1, G2 of H is equal to G1, G2, H, G1, G2 inverse. And that is equal to G1, G2, H, G2 inverse, G1. And that is G1, G2, H, G2 inverse, G1 inverse. And that is equal to G1, G2, H. So this map is a group action. So let us compute GH. This is an isotropy subgroup of G containing H. And what is this? This is G belongs to G such that GH, and that is GH G inverse, is equal to H. This is the expansion of the definition of the map, and this is the definition of isotropic group. Is a subgroup of that is actually the isotropy subgroup containing H. So this is what? This is actually GH contains H. Why? Because every element of G, if you put it here, this is going to be C. And H is normal in GH. Why? Because this is the definition of the normality. And GH contains all elements in G that leaves H invariant under the action, under the group action. Implies GH is the largest subgroup of G having H as a normal subgroup. So you are taking all the elements of G, that satisfies this. There is no other element G in G that satisfies this. So this is the biggest or largest subgroup of G containing H and having H as a normal subgroup. This subgroup of G is called the normalizer. Normalizer of H and is denoted by n square bracket H. So if H is not normal in G, then this is the largest subgroup of G having H as normal. If H is already normal in G, then these two are same. The normalizer of H and G are same. Now the next attempt is to find out a relation between the index of G of H and the normalizer of H, the index of the normalizer of H over H. That is our next step. So our next attempt is to find out a relationship between the index of a subgroup over a its normalizer and its index over the whole group when the subgroup is a P subgroup. So the theorem is like this. Let H be a P subgroup of G. P subgroup of G. Then the index of the normalizer over H is congruent to the index of G over H mod P. Here the word P group is very important. P group means P subgroup. H is a P subgroup means H itself is a P group, meaning every element of H has an order of a power of P. Here P is a prime number. So let us try to prove this. So what we do is let L be the collection of all left cossets of H in G. See, H is a P subgroup, meaning H itself is a P group, meaning the order of H should be of the form P to the power of n, and that is a corollary of the Cauchy's theorem. Okay, we are going to make use of this and our first result in this chapter. Okay, so here L is the collection of all left corsets in H. Now we will define a map. Define a map from H cross L to L. Basically what we are going to do is we are going to define a group action on L by take an element H and take an element from here. This contains left corsets, so it will be of the form HX, sorry, XH, and that is equal to, our definition is HX. This is also a left corset, so it definitely is in here. So this is a group action. We still have to verify it, but I will leave it to you. Now L, the order of L, the collection of all left corsets, is nothing but the index of G over H. Okay, and what we are going to do is we are going to find out, see, LH L contains, sorry, H contains P to the power of n elements, and L is a finite H set. Then from the first result we have the number of elements in L is congruent to LH mod P. But we know that LH is this. So, and with this result, we can always write it as LH is equal to L. And what is LH? Let us see what happens here. This is elements from L, that is XH, such that it is mapping. See, how do you define xg is x belongs to x such that gx is equal to x. So x belongs to L, x belongs to L such that gx is equal to x. So that means hx is equal to, for all h in H. Right? Our idea here is to find out the elements x such that this condition is satisfied. Where are these elements x? So let us expand one more time. Hx belongs to L such that this actually you can write it as x inverse h x of h is equal to h for all h in h. What does this imply? This implies that x inverse belongs to n of h. What is the definition of n of h? All elements in x such that all elements in G such that G inverse belongs to H. Then G belongs to n of H. That is a normalizer of H. And this implies X belongs to n of H. Because NH is a subgroup. So if X inverse belongs to NH, X belongs to NH. So what does this mean? This means that this X is coming from n of H, meaning L of H is equal to the left cossets of H in n of H. And that implies the number of elements in LH, that is actually the number of one element orbits containing H, is equal to the index of normalizer over H. Now we apply this rule, this result. So we'll have L of the number of elements in L is this. So from 1, 2 and 3, from 1, 2 and 3 we have G of the index of G over H is congruent to the index of the normalizer over H mod P. So before we start our first Sylow's theorem, I have one more result to go, and that is a corollary of the previous theorem. It's very simple, but let's go through this. Let H be a P subgroup of a finite group G, and P divides G or the index of G or H, then the normalizer is different from H, meaning there is a proper normalizer of H. This is a subgroup of G properly containing H. Okay, the result is very simple. The proof is very simple, but the result is very powerful there, because if P divides the index, then you are assuring that there is a normalizer that contains H. Using the previous result, we have what we have is G of H is congruent to NH over H mod P. P divides G of H implies P divides N of H over H, and that implies N of H is different from H, because if P divides, because P is different from 1, P is not equal to 1, P divides this, so this is actually a multiple of P. So there are left corsets here. Trivial, non-trivial left corsets. So the normalizer is different from H. Now let us discuss the first Sylow theorem. First Sylow theorem. Let G be a group of order P to the power of n times m, where P does not divide m. P is not a factor of m. Then there exist, the first one is there exist subgroups of G of order P to the power of I for all I from 1 to n. The second result is for every I, the subgroup of order P to the power of I is a normal subgroup of a subgroup of order P to the power of I plus 1. So, meaning, let us take an example here. Suppose the order of G is equal to 24, and that means 2 cube times 3. Let us not take 24 because I don't want to make 3 different. So let us make it as 40, and that is 2 cube times 5. So this satisfies all the conditions here. Here P is equal to 2, n is equal to 3, m is equal to 5, and P does not divide 5. So all the conditions are satisfied. What the theorem says is that for every I from 1 to n, from 1 to 3, we have subgroups. That means G has a subgroup of order 2, order 4, order 8. And let us take this as H1, this is H2, and this is H3. So for H1, we can find that not necessarily this H2, we can find a subgroup, let's say H2 dash of order 4, such that H1 is normal in H2 dash. And that is what the second part is saying. Similarly, you can find another H3 dash of order 8 such that H2 dash is a normal subgroup of H3 dash. Now let us prove this theorem. The proof is not very complicated. It uses previous results. The first part of the proof is done using the mathematical induction, meaning that we are going to show that there exists a subgroup of G of order P, where P I is equal to 1. Then we'll assume that there is a subgroup of order P to the power of I where I is strictly less than n. Then we'll show that there exists a subgroup of order P to the power of I plus 1. Sorry, I plus 1. So the first part of the mathematical induction is very simple here, because we have given that the order of P is equal to P to the power of n times m, implies P divides G, and that implies by Cauchy's theorem there exists a subgroup of order. So the first part is very simple. For I is equal to 1, there exists a subgroup. So I assume that there exists a subgroup H of order P to the power of I, where I less than 1 less than or equal to I strictly less than n, of G. And that implies P divides G of H, because I is strictly less than n. And that implies P divides n of H or H. And that implies n over H is different from H, and H is normal in n of H. So now consider the canonical map gamma from n of H to the factor group NH over H. So since P divides NH H, P also divides the order of the factor group. And that implies by Cauchy's theorem, again, there exists a subgroup of order, subgroup K of order P. So that implies gamma inverse of K is a subgroup in the normalizer of H containing H. And that implies a gamma inverse of A, K, is of order P to the power of I plus 1. Because P divides this index, or P divides this factor group, y of k have to be an order P to the power of I plus 1. And that completes the that completes the first part of the theorem. Second part, we know that H is less than or equal to, at least strictly less than, gamma inverse of K, which is less than or equal to H. So since H is normal in N of H, see here we only showed that gamma inverse of K is a subgroup of N of H, and that implies gamma inverse of K is a subgroup of G. Okay. So here we know that this is true. Since H is normal in N of H, H is normal in Y, gamma inverse of K, and that completes the second part. This is an order of p to the power of I. This is an order of p to the power of I plus 1. Since this is normal, H is normal in N of H, H is also normal in here. So that means p to the power of I, the subgroup of order p to the power of I is a normal subgroup of this group, which is of order p to the power of I plus 1. And that is what the second result is. And that completes the